Here is a presentation of iMTSP solving min-max multiple traveling salesman problem with imperative learning. Multiple traveling salesman problems, or MTSP, seeks tools for multiple agents such that all cities are visited exactly once while minimizing an objective function defined over the tools. It arises in numerous robotics topics such as automated agriculture and warehouse logistics. Solving large-scale min-max MTSP is challenging due to its NP-hardness and non-convexity. Classic non-learning methods suffer from exponentially growing computational burden when dealing with large-scale MTSP. Deep learning approaches can relieve the computational burden, but it is hard to incorporate constraints like collision avoidance to the models. One way to achieve efficiency and to impose constraint is combining deep learning model with classic solvers. However, optimizing this kind of model is very challenging. The proposed iMTSP framework includes an allocation network which decomposes an MTSP into several TSPs, and a solver module which solves the resulting subproblems. We use a control variate-based optimization algorithm to provide stable gradients to the allocation network through the discrete allocation space. The idea of control variate is to introduce a new variable that is correlated with the original one, which is the actual gradient in our case. By exploiting their correlation, we can design a new estimator for the original variable with less variance. The figures visualize the performance of the baselines and the proposed model on two instances with a central depot and an off-center depot respectively. The numbers denote the length of the route, and different colors represent different agents. iMTSP always produces the best solution and has fewer suboptimal patterns like circular partial routes or long straight partial routes. Performance comparison on test set is shown in the table. iMTSP provides solutions with overall 3.2 ± 0.01% shorter maximum route length comparing with the reinforcement learning baseline, and has very evident advantage over the Google OR-Tools. The figure on the right shows the gradient variance history of our method and the reinforcement learning baseline, with two different settings. Our gradient estimator converges about 20 times faster than the reinforcement learning baseline.